Okay, so let's code it up this ID3. So here we're using some basic function in pandas. So so you also need to know how to program in and with the pandas as well. So this is very important and a skill set. So we are going to work on this tennis data set. And I already coded up for this tennis and typing all these like data here. You have like outlook, we have a temperature, we have humidity, we have windy, and we have play. So these 4 features, and the target is play. So the way, so you want to like see and to get the first row of the pandas, it's like dot location of 0. So basically to get the first row of the data set, right? And you can also says, okay, I want to extract the like data frame. So these are, I'm actually, I'm the tables. So you can manipulate and you can make manipulations on the tables. For example, you can say, I only want to get the tables with outlooks equal to sunny. So you are going to extract the and a condition that outlook is equal to sunny, then extract the corresponding data frames such that everything here will be, the outlook will be sunny here. So the reason that I said reset index job equal to true, that means, if we don't have these things, they will keep the original index. But if we change this, index, and it's like set, it's like reset index equal to true, then so the index will just start from 0 again. So the first thing is we need to put in this, like calculate this like entropy. So this is obviously a very important function to start with. So that means we are going to get the target. That's the most important things. Right here, in this case, that would just be the last column of my data frame. So I'm going to get the unique value, which is yes or no. That I'm going to calculate the fractions of and for each unique values for yes or no. So these are just calculated fractions. I'm adding this like p log ppi log pi, and it has to be log and base 2 here. So this is I'm actually output the entropy data, but we already calculated by hand, so we know this is the value is 0.94, which is matches with our and hand calculations. Also, this is also like, and this function is to calculate the conditional entropy of each feature. So this is kind of like slightly more complicated. So the first thing, we still need to find the unique target values, which is yes or no in these cases. And also we need to find the unique value for the features, which is f values, right? So, and all these f and the value information here. So right here we have and we have to loop through all the variables, which is all the f's. So what we're going to do is we're going to get and the numerator is, I want to remind you right here. So my numerator right here is the number of the set with my feature f is equal to f, and it divided by the denominator is number of the and the data of and of the whole set S. So right here, so that would be, and on the top that would be and that would be so, and the features be, and I want to like extract the features being the variable, and also I'm going to loop through all possible target variables, which the target equal to the corresponding target variables. So this will be my numerator, and of course the denominator, that will be all the possible and a set of the features being the corresponding variables, right? So this is being like we are restricting our set that my and my set has the and my corresponding features equal to the variables here. So we find out the fraction right here. So these fractions, I need to plus small tiny numbers to ensure this is not dividing by 0, just in case. Then we calculate this and a fraction times log 2 fractions again. Here I'm adding this epsilon to ensure again this is we are not doing the log of 0 here, which is not defined. So this is basically the entropy for each feature. Then I'm going to weight them out for the all possible and F values and with the corresponding weight. With that, that will be giving you this conditional entropies for each and of each feature. So this is like slightly complicated, but you have to think through what is going on, why we have a like double loop here. So we have a like outside loop is we loop and through all possible of F. The inside loop is we loop through all possible of target, which in this case is just being yes or no. And at the end, we like calculate fractions, we calculate this and conditional entropies altogether. And of course we can, and we know this is the feature that we have. We have all these 4 features. And the last one is the target. So we exclude that. In this case, we're going to calculate all these entropy for so conditional entropy for each and of each feature, right? You can calculate right here. It actually matches to our and calculation right here. So you can see, I think we already calculate this temperature one by hand, which is 0.911. So it actually matches our calculations. So it's always a good practice. So once you write some code and you just calculate one specific cases by hand to see whether it actually matches your calculations. Then we're going to calculate this like information gain. So I mean, this is quite straightforward. That information gain is the total entropy of this data frame subtract the like conditional entropy of that particular features. You loop through all possible features, then you will get information gain of each features. So from this, you can see the outlook has the maximum. So information gain. So that will be the outlook will be the root of the of my decision trees. Okay, so this whole code right here is it's how we do the decision trees. So we are using so like recursive methods. So this is something that is pretty interesting, and slightly difficult to understand. But this is basically a DFS approach, depth first search approach, and here is how we do that. So first we need to have a separate functions. This separate function actually is to get subtables. Once you specify your particular node is equal to some variable, you are going to extract the sub data frames for all the node equal to variables. Again, so this is the command that actually this 20 command is how we actually build up this decision trees. So the first thing is we need to set up the target, and we set the features. So, and this is just being the last column for the target. So what you do is first things you get the features with a maximum information gain, and that will be your node like root of your decision tree. If this tree is currently empty, you're going to create a dictionary as your tree. So this is how we actually build a tree directly. We're trying to using the dictionary structures to build the trees. And of course, this is not what like supposed to be done. When you do the scikit-learn here, and when the scikit-learn is doing, so this is just to do some illustration of what it's doing right here. In scikit-learn, they're using much more complicated ways to build and build the tree structures. This like dictionary things is just to do some like simple illustrations. Here is we are going to loop and make loop to construct a tree by calling this functions build a tree and recursively. If we check the subset is pure, then we stop if it is pure. So basically, we are going to loop through all possible variables in the variables. Then we get the corresponding sub like tables, and this unique functions is I'm going to count how many like unique values of the target right now to see like and how many being like plus and how many being minus. If it is count equal to and count equal to 1, that means so the whole thing is being pure. That means they are either getting all positive or negative. That means I'm going to assign the and leave to that like specific node. So that means I'm going to stop right here. So this is tree node of variable is CL value right here. So that means this is, and we only have 1 values, right? So this is being like either plus or minus. If this is not pure, and if this subset is not pure, then I'm going to call this function recursively of this subtable right here. So basically, we are going to take this subbranch, right, right here. Then I'm going to call this subtable and with the functions like recursively. So we are rebuilding these functions with DFS approaches. So this is a very convenient way that we call this function recursively. I mean, runs right and pretty fast. It can build all these trees and automatically. And you can see everything like what we talk about is just like building, right? I mean, this line right here. So we get the information gain and trying to create a node that with the maximum information gain. So these are actually the only two and the 2 lines that contribute to the as ID3 and algorithms. So I mean, after that, we will build a tree which is T look like that. We can use in pp-print to actually print out this dictionary. So if we actually print out dictionary, you can see this tree right here is precisely equal to what we already showed previously in this and in this diagram. Here we have 2 layers. We have a first layer and using Outlook, the second layers we check humidity and the wind. Right. So this is basically what we are getting. This is perfectly matched to what we already calculate by hand. So this is basically the tree that we should be getting here. Okay, so let's perturb this data a little bit. I'm going to add in 1 like additional entries with the sunny, hot, normal, strong, and no. Right. So we just adding 1 more data. So now we have 15 data. With the 15 data, we just run this again. It turns out in this cases, we have additional 1, 2, 3, 4. Additional now my trees becomes has 4 layers. Right. So I mean, this is something that is quite interesting. I only add 1 more data entries, then my data trees changes dramatically. I mean, as a comparison, you can see previously here we have and humidity here. By adding 1 data, and they start to check the temperatures. And after temperatures, they're going to check the humidities again. Right. So this is something like an additional layers that being like introduced here. So this extra complexity may not worth it. It could lead to overfitting if this test data follows the same patterns as previous training data. So what you can do is you can do some like prunings, or what you can do and you can do some cross validations to find out what is the best and the best choice of the layers and for the decision trees, right? So this is we have talked about the cross validation before. But in this problems in decision trees, the hyperparameters in decision tree is the number of the layers that you can force. Like say, I only force my and the decision trees to have only 2 layers, then actually you probably will just stuck with this and decision trees right here, because that probably can give you the best result. Here, the reason that we're getting, such complicated entries is because we enforce our subset to be pure, right? So we don't, and we enforce all my training error to be 0, which is unrealistic, in practice. So that's why, in practice, what we do is we're going to go through all possible and a layer of decision trees to ensure and to cross-validate to find out the optimal and the layers of decision trees. So this is usually being discussed in detail in 593. So we will not, get this in detail, this courses, but just, for this courses, the main goal for the part of decision tree is to understand the algorithm, how they train this decision trees in, certain like greedy and algorithms, and what kind of metric they're being used here. So let's try a different data set here. And also another way is you can do some pruning if you need it. And this is another data set. It's just, it's a very popular. It's basically, it's bank is want to give, and whether they approve this, credit line or not. So you have a collateral, you have income, you have debt, you have credit histories. Then the target is the risk. If the risk is high, you won't approve any, and the credit line and so on. So this is your pandas data frame. And then what you do is you just plug in this and build tree, and which is the function that I built using the information gain to find the most relevant features and the most relevant features. And we build the decision trees by ID3 algorithm. So you can see that, this actually build the trees automatically. The first, the root will be the income. If income is low, that will automatically be high. If it is 15K to 35K, so first thing, and the next part is we're going to check the credit histories. If credit history is high, bad, that will be high. It's good, that will be moderate. If it's unknown, then we check the debt. If it's high, that will be high. If it's low, that will be moderate. Then, for the income is over 35K. Again, this next, we're going to check the credit histories. If it is bad, that will be moderate. If it is good, that will be low. If it's unknown, that will be low. So this just gives you some idea how this things is being processed. And if you are giving such data set, which is 14 entries, this decision tree right here give you a bunch of rules to tells you what kind of and the rules that you should be following based on the data, right? So and this decision tree just give you a set of rules to tell you what you and how you should think and how you should make a judgment based on the new data's entries, right? So this is basically I learn the rules from the data, right? So that's the that's the advantage from the decision trees. Every decision trees can be explained, right? So it can be rationalized. Unlike other algorithm, for example, like logistic regressions, like neural networks, all these kind of things, we cannot rationalize it, and we don't know why this is being being made such bad and such good or such bad decisions here. But for example, if we follow this whole idea to determine this guy has a low risk, it's the reason is because his income is over 35K there, and his history is good, so that will be low. So that will be the reasoning, and it can that I can provide proper reasoning. If this guy has and very and the risk is high is because the income is between 15K to 35K, and history and credit history is also bad. That's the reason. I can provide the reasons why we and predict this guy to have a high risk instead of others. All right, so that's everything I want to talk about, and that's how we implement the ID3 from scratch.